In this lecture, we will discuss applications of Gauss law. This is the second part in continuation of the first. In the first lecture, we have discussed some applications, and now we will extend to some more details. In this lecture, we will be able to learn calculation of electric field due to two parallel charge sheets, and we will also discuss application of this arrangement in development of capacitor. Gauss law has many applications. We have discussed some application in the previous lecture and some we will discuss here. We know that the Gauss law can be used to solve complex electrostatic problems. The problem involving unique symmetries like cylindrical, spherical or planar symmetry. Also, there are some cases in which calculation of electric field is quite complex. If you are having large number of charges or the electric field calculation is complex, that involves tough integration, so it will require a lot of time. Gauss provides an alternate. Gauss can be used to simplify evaluation of electric field in a much simpler way. We can apply Gauss law in many ways. Like, first thing is, if we want to calculate electric field using Gauss law, choose a Gaussian surface such that the evaluation of electric field become easy. Make use of symmetry to make problems easier. Remember, it is not necessary that the Gaussian surface to conclude real surface. That many times the Gaussian surface do not coincide the real, and it can be inside or outside the Gaussian surface. We can take these steps to calculate electric fields. Now we are discussing some examples from the electric fields calculator. In the first lecture example, we will discuss electric field due to two parallel charge sheets. In the last lecture, we have discussed electric field due to single charge sheet, and we know that the electric field always in the outward direction if the charge is positive on the sheet, and it is inward direction if charge is negative. And the area, unit area, whenever we always consider outward side from the sheet. Using these laws, we can calculate the electric field due to two parallel charge sheets. As far as importance of this application is concerned, it is very important application in capacitors, and so we'll try to learn these things in the next example. As we have taken a condition, consider two plates, infinite sheets with equal and opposite charge. On the plate, I am assuming the first plate as A and second plate as B. Now on first plate I am assuming only positive charge is given, so the charge density is positive sigma, and similarly on the negative second B plate we have given negative charge, so the charge is minus sigma. Now we have done the calculation of electric field in the last lecture on plane sheet, and the magnitude of electric field on either side of plane sheet is always equal to sigma over 2 epsilon 0, that we have done in the last class. So if we want to learn, we can go through the last lecture also. So these are the two plates. Now the as we know, the it is always directed outward when the charge is negative. Sorry, when the charge is positive, and inward when the charge is negative. Yes. Here in the case in the plate of A1, the charge is positive. So all the time, if we are considering the field due to A is E1 and field due to B is E2, then from A the charge is always outward side. Here we can also draw this like this, but we don't get no uh, we don't have requirement of this, but it's outside. But on the other side, as far as second slide sheet is concerned, in the second plate the charge is inward due to negative charge. Both are inward. Now we want to calculate electric field at various positions. So in our case, we will consider two cases. To first, when the we want to calculate the electric field between the two plates, and second, when towards right you want to calculate the field P2, or you can also calculate here towards left P3. You can also calculate. When the point P1, the first point, which is between the two sheets, if you want to calculate that there, the field, try to get the things. At point P1, two fields are there. Due to positive, positive is always outward, so it is on the this side, and due to negative, negative is inward, so this side. So ultimately both will add. Can you check this? On P1, both the fields E1 and E2 both are in same direction, so both will add. We have studied in the last lecture, and we know this, the electric field due to charge sheet is always sigma over epsilon 0, and direction is same in both the cases, so the field will be sum of the two. And due to this, the electric field, if you calculate total electric field, that electric field is E1 plus E2, due to where E1 is the electric field due to first and E2 is the electric field due to second shade. Since both are in same direction, we are saying that both are in same direction, and due to this we are adding these two. Now we know the value of first is sigma over 2 epsilon 0, second is sigma over 2 epsilon 0, then the sum will be this sigma over epsilon 0, and the resultant, since both are in the same direction, resultant will be in the same direction towards the right. So in this way we have calculated the electric field between the two plates. You can write this statement in this way. Suppose you are having two uh, parallel sheets and you are giving opposite charges on different sheets which are parallel to each other. If you supply some if you supply positive to the first and negative to the second, then the electric field on the center of between these two plates is sigma over epsilon 0. There is another case. Suppose we want to calculate the field at P2, which is outside the sheet. Of course, this may be here or may also be here. On the left hand side. In the right hand side, E1 is in one direction and E2 is opposite direction. Both are in opposite direction. The electric field will be equal in magnitude and opposite in direction. So the resultant can be done as E1 minus E2. And that is why, try to understand this. One field is in right hand side and second is in left hand side. Here I am marking here E1 and E2. And due to this, the answer will be 0. Since both are in same direction, there is no field here. Similarly, we can also calculate this for this side on left hand side. On left hand side again, E1 will be in outward direction and E2 will be in inward direction. So both will be 0. That is why we have concluded a very interesting result, that whenever we have two plates, parallel plates, and we have supply opposite charges to each other, then there is a field between these two plates which is more than the individual, but outside the plate there is no field, it is 0. We can think over various application of this law. We have discussed uh, field calculation in infinitely sheets and parallel sheets. Yeah. And these arrangement can be used as an application in parallel plate capacitor. This arrangement has huge application, as we know that parallel capacitor is one of the best invention, and it is used for charge storage. In the parallel plate capacitor, as it's clear from the name, we have two parallel plates, and these parallel plates are formed by arrangement of electrodes and insulating materials or dielectrics. These dielectrics or insulating materials generally be kept in inside the parallel plate capacitor. A parallel plate capacitor can only store a finite amount of energy before dielectric breakdown occurs. And this can be defined as when two parallel plates are connected across a battery, the plates are charged, the plates, and an electric field is established between them. This setup is known as parallel plate capacitor. As I told you previously, this is an application part of our these two infinite parallel plane plates with some charge. You can see here these are two plates. On one plate we are keeping the charge plus q, and on another plate we are keeping the charge minus q. The distance we have kept as small d. I'm talking about arrangement of the parallel plate capacitor. Now these plates are having the area is A. We can add dielectric between these two if it is needed. Normally we need it to store, to increase the storage, increase the energy. The important thing with this parallel plate capacitor is the plates carry an equal and opposite charge. If the first plate carries a charge q and the second plate carries minus q, and we assume the area A and the distance between these plates is d, and as we are saying the total charge is q on the first plate, then the charge density can be written as sigma q over A. Similarly, if we calculate the charge density on the second plate, this will be minus q over A. So these two are the charge density, and we are taking this is like this. We are having these two. Plates. Now we have given the value of sigma to this and to this, which is q over A and minus q over A. Now we can divide the region around the parallel plate capacitor into three parts. Suppose this is your parallel plate capacitor, then we can divide it three parts. First part is area left of the first plate. Second part is between these two plates, and third part is right side of the plate, second plate. So now we can use the Gauss law to calculate the electric field in these areas, as we did in the past in the few slides. In region 1, the magnitude of electric field due to both the infinite plate 1 and 2 is same as at any point in this region, but direction is opposite. We have discussed these things in detail in the previous slides. Because the field due to this may be Suppose I am taking here these plates and the plates are having different color to analyze you. Now the field due to first will be this and this, whereas the field due to this will be this and this outward side. But this is possible when both are plus. In our case, this field is minus, as if in our case here we are having minus q and here we are having plus q, then the field will be like this. So we should keep in mind that the direction of field depends on this direction. Now if this is minus, then here it is also opposite direction. Okay, and similarly if you want to plot the field here, this will be this. Mind this is everything is depends on whether the charge is plus or minus. Now you can see this. In the first case, these two are in opposite direction. Since these two are in opposite direction, the answer will be 0. No field in the left side. But in the second region, if you take these two, one is plus, so plus means this direction, plus means this direction, and second is minus, so minus again this direction. These two are in the same direction, these two will be added. If you add this, you will get the answer like this. The electric field will be added in this region. However, when you move again to the third region, the region of this plate, parallel plate capacitor, then again you will see in the third region, then this will be in this direction, or the field due to second will be in opposite direction, like this. And these two will be cancel out each other and you will get answer 0. This example tells you that by using the parallel arrangement, we can develop capacitors and the electric field can be calculated by Gauss Law. In this lecture, we have studied the parallel plate arrangement, infinite plate arrangement, and calculation of electric field and the application in capacitance. Thank you.